Hello, this is our week 4 part 2 assignment, high frequency words, for the group of Austin Chan, Justin Herman, Deepak Mongia, Michael O'Donnell, and Chester Poon. So for this assignment, we decided to analyze the word counts from John Steinbeck's East of Eden, a timeless American classic. East of Eden is about a man, aimless but hopeful, as he struggles with sin and misfortune throughout his life in a post-Civil War America. So I particularly like this book because it has a pretty rich vocabulary and there's a lot of interesting words and phrases that are good for analysis. And so the book's pretty long too. It's 500 pages, so there's a lot of words to count in this one. So to start, we loaded a few packages, primarily requests, pandas, matplotlib, NLTK, ggplot, and scipy and numpy. So requests is a package in Python that lets you fetch things from the web. Pandas it imports data frames like an R. Matplotlib is used to plot graphs and figures. NLTK is used to do our natural language processing, so like stemming and counting words and stuff like that. And then ggplot is used to make some of the plots. And then here are some of the other NLTK specific things like the tokenize function, some stop words, and a stemmer. And then scipy and numpy are used to calculate the Zipf's law function, which is a function we'll compare our word counts to at the end of the analysis. So fetching the text was pretty straightforward. All I did was get the text from the archive.org website, and I posted it onto GitHub, and then all this does is just take the text directly from my GitHub and then puts it in here. And so here I call this request.get URL, and I specify the URL, and then I get the text from that URL and store it into this corpus variable. So processing the text. So for our analysis, we considered a unique word to be a lowercase word stem, because there's a lot of like little variations in words, like capitalization and kind of here in this example we have eat and eaten, which are technically different words, but they mean the same thing just in different verb tenses. So we want to make sure that words like these are counted as the same word. So when you lowercase them, and make sure that capitalization doesn't separate or count two words separately. And then when you stem the words, it turns words like eaten into eat. So then now you have these two, eaten and eat, and they're both turned into eat. So that's pretty convenient. So all that this code does is that it uses the tokenize function from the NLTK package, and then it tokenizes the corpus, which all that means is that it separates the words in the book into separate items and then each list. And then here is a list comprehension that lowercases all the alphabet characters. So then if there's a non-alphabet character as its own item in the list, it will just remove it and then it'll lowercase it. And then after that, it gets stemmed using this Porter stemmer, and the link to that stemming algorithm is over here at this link. And then so then we have a list of stems for every word in this book. So then counting the words. So here I've just made a function that counts words. So here I specify, or I initialize a dictionary object, and then I write this for loop that just iterates over every single word, and then adds it to a count every time it encounters a word it's seen before, and then adds a new word every time it encounters a word that it hasn't seen before. And at the end, it returns the counts. So then all I did was run this word counter on the stems and stored it in this word counts variable. So for the analysis, we were asked to answer a few questions, primarily finding the number of total unique words in the corpus, the number of unique words that make up half the number of total words, and the 200 highest frequency words, and then comparing these words to Zipf's law. So with the unique word count, this is pretty straightforward. All I had to do was just find the dimensions of the data frame of the stems, or of the word counts, sorry. So here all I did was just order I put the dictionary into a pandas data frame, and then I ordered it in ascending order, so the words with the highest frequency would show up first, and then I just called the shape function, which just shows you the dimensions of the data frame. So then in here it just says there's 12,708 rows and 2 columns, so that just means there's 12,708 unique words in the corpus. So unique words that are half the total word count. The way I calculated this was I just took a cumulative sum of the word counts, and then took the proportion of those cumulative sums to create a cumulative percentage. So it turns out that at about word 63, we have 50% of the words, so about 94,108 words, and the way I got that was that there's 187,455 words in the total corpus, and so dividing that by 2, you get about 93,700-ish. So one thing to note is that Python's indexes start at 0, so even though here it says 62, it actually is the 63rd word, and that's seen here, so at 50%. And that word is get. So comparing to Zipf's law, all I did was I took the ordered list I had previously and just took the first 200 elements of it, and then calculated the relative frequency of those 200 words. And then here, all I did was create the Zipf's law function for between 1 and 200, and then I plotted both of those lines here. So in the red is the Zipf's law function, which is like a pretty good curve, downward curve, and it's pretty perfect. And then here on the blue line, this kind of jaggedy line, that's the actual word distribution of the book. So as we can see, it follows it somewhat closely. The main difference here is in between all this about 2 to the 25th or 50th word, there seems to be a higher frequency of these words compared to the Zipf's law function. But otherwise, it follows it pretty closely. So I would say that it's Zipf's law is an accurate fit for this particular book. So comparing this to other corpora, most corpora share a lot of similar words, what we would call stop words. So a lot of these words are like the and a and to, and like pronouns, which don't really contribute much towards the meaning of the words, and often are kind of like these bridge words in the English language that are used a lot but don't really mean anything. So they're common in this book, as they are in pretty much all corpora. But once we take those out, we can kind of see that there are some differences. So in here we have words like said, and then Adam, which is the main character's name, then no, and like, and would, and could, and Lee, which is another character's name. So a lot of verbs and a lot of characters, which should indicate this is kind of like this is a story. And with stories, it usually involves characters going places and doing things and kind of moving the plot along, whereas compared to like tweets or something where it's just people talking about themselves, or maybe like a textbook would talk more about specific terms and definitions and things like that. So kind of the main differences between this corpora, or this corpus, and other corpora is just that by the fact that it's narrative fiction, it kind of adheres to certain word patterns involving characters and verbs, versus other corpora which may use other words depending on their genres. So yeah, that is our week 4 part 2 high frequency words assignment.